Alright, in this video we're going to be looking at regulated power supplies. Now to begin with, I'm actually going to show you an unregulated power supply. And this circuit here below is nothing more than what you've seen probably in your first year courses. So we have a transformer which takes some AC voltage in, typically 230 volts AC, RMS, might be, for example, 10 to 1, so we get down to 23 volts AC. We then pass it through a full wave bridge rectifier and a filter or smoothing capacitor. So this circuit is nothing more than an AC to DC power supply where we have AC coming in and DC coming out of it. Now what you probably didn't study was the effect that two conditions have on this circuit and how they affect this value here and where it gets its name unregulated. So the two things we're going to have a look at is how a change in Vin affects the circuit, and also then a change in the output current. So a regulated power supply has constant output voltage regardless of changes in V in or I out. So within practical operating limits, the regulated power supply, even if we change the amount of current we're drawing, we should get the same voltage out, and even if we change the amount of voltage coming in, we should get the same voltage out. So that's what we mean by regulated. If we come back up here and actually have a look at this circuit, we see that if, for example, this voltage here goes up, so let's say it goes up to 240, we'll now get 24 volts here, approximately 0.9 times that will give us the DC voltage, which will be approximately 21.6 volts here DC. If we do it with the original calculation, alright, be 23 times 0.9, we would have instead, I'll do it in blue, 20.7 volts. So it's very easy to see by having a look just through the circuit how a change in the input voltage, even as 10 volts here through the circuit, is actually going to give us a reasonable change, almost a whole volt of change out here in the output. So we would say that this particular circuit has poor line regulation. Alright, and where that term means change in Vin causes a change in V out. So a circuit with good line regulation, regardless of what the input voltage does, we should get a constant output voltage. Alright, so regardless of changes in Vin, so that's one of our regulation parameters. We can also look at this circuit and go, well, what would happen if our output current changes? Now, this circuit has a particular feature that if the output current increases, we actually get a curve that looks something like this. So if this is V out and this is I out, you'll actually get maximum voltage at no current, and as you increase in this direction your output current, the voltage you get will actually decrease. Alright, this is quite typical of an unregulated power supply. This circuit therefore then also has poor load regulation, where poor load regulation is changes in I out, so the output current causes a change in V out. So in both cases we're interested in keeping the output voltage the same. That's what our power supply is designed to do, give us a constant output voltage. But depending on whether we change the output current or we change the input voltage, this particular circuit will actually give us a poor output voltage because it will be changing with both of those parameters. Okay, motor's going at different speeds, therefore we get a different voltage. We don't want that. All right, the voltage coming in is going to vary. You know, we're not getting 230 volts the whole time, so we're going to get differences caused by just being plugging into the mains in our house, or wherever that voltage happens to come from. Right, so the two terms that you need to know here are line regulation, which is related to changes in input voltage to changes in output voltage, and load regulation, which is changes in output current versus changes in output voltage. Right, so those are our two definitions. So moving forward, let's look at how we can solve this problem. And using this circuit up here alone is not going to be the solution, unless you have a particularly unique situation where you have a constant load with a constant input voltage. Then it works fine. We can use an unregulated one, but generally we're going to have a situation where the load's going to change and or the input voltage, and therefore we need a regulated power supply. Now, one of the simplest solutions is what's known as a Zener voltage regulator. Now, we all know with a Zener voltage we're going to have a voltage when connected in reverse bias that is fixed when looking in parallel with that device. So the voltage across that Zener will be fixed once it exceeds it within operating specifications of that Zener. Alright, so remember, we have a look with the Zener diode, that when we operate it in forward bias we get the normal diode. So sorry, that's current, that's voltage, and this is forward bias over here. Get the normal diode response, but when we operate it in the reverse bias we also get this knee voltage here, or Zener voltage, where it will actually keep that voltage and allow current to flow through it. Now, the downside to this particular configuration is that the poor old Zener diode is having to conduct quite a lot of current. So, big disadvantage. Okay, the Zener gets hot. So, for the Zener voltage regulator, it's only suitable really for low current power supplies. It's not really useful for anything else, and it's not very efficient either. Alright, so the Zener gets hot, therefore low current only. Furthermore, the design of this particular circuit relies on the fact that you have a constant load. So another disadvantage would be that this is really only suitable if the load here connected to your output terminals is constant. Otherwise, you're going to end up with problems where this device is going to overheat and you're not going to get the expected output voltage. Part of your design takes into account a constant of the load current. Right, so constant load only, so we will have poor load regulation. But it does have reasonable line regulation. We also have to watch out that if you actually remove that load completely, then all of the current's going to flow through our poor old Zener diode and you're probably going to blow it up. Alright, so this is a low current, simple but inefficient solution to our problem. Right, we're not gaining a whole lot by using the Zener voltage regulator, but it does exist and it is used. What we're going to do instead is we're going to keep all of our existing circuit. Alright, so everything on this side is the same as above. And what we're going to do instead is add in one of these, what's known as a 3-terminal voltage regulator. And they can look like any normal IC basically, but very common are they in these TO220 packages. Alright, so very, very common that you pick up a device that looks like this. And the only difference is that it gets connected in series, so V in, V out, and to ground, and we have an extra filter or smoothing capacitor on the output. Now, by doing this, this circuit is now a regulated power supply. So we've taken the same front end effectively, right? We've still got our transformer, our bridge rectifier and our smoothing capacitor, but we've added onto it in series the 3-terminal voltage regulator and an extra filter capacitor. And we've now turned everything on this side is unregulated, everything on this side, well, basically from this point on, I should say, is now a regulated power supply. So we've actually fixed this problem. This is regulated both load and line. So let's have a look how it actually does this. If we come down to this block diagram, which is this device here, or can be a range of devices, but they're commonly a block diagram would look something like this of their internals. So this is the internals of that 3-terminal device. What we see is we have a series passed element which is controlled by an amplifier, and we have some feedback, right? So we've got some major components in here, which actually is a little mini control system. And so what happens is that this series pass element controls the output voltage by internally dropping it. So effectively, this device here looks like a variable resistor, okay, in the sense that it has a variable volt drop across it. And by being able to vary the volt drop across this device, no matter if this voltage changes or the current changes, we're able to maintain the desired output voltage. Okay, so internally dropping it, so the internal feed drop of this device. Now, how much do you drop internally depends on what your output voltage is. So a fraction of V out is fed back to, alright, so here's our voltage divider. It's a precision divider, so it's all internal, and that's set up, fed back a fraction of that to an error amplifier. Now the error amplifier compares the fraction of V out to a reference voltage, this guy here, which is very, very accurate, and it compares the difference between those two. Alright, so voltage coming in there versus the voltage here. And depending on whether this fraction is greater or less than the reference voltage, it then applies a control signal back to our series pass element, which then allows it to adjust the voltage drop in order to maintain it at our desired output range. So these four components, effectively, the series pass element, which is like a variable resistor, the precision feedback resistors, which provide a fraction of the output voltage back to an error amplifier, which compares it to our voltage reference, and then uses that to control at the series pass element. Not only that, but many of these devices have things like thermal protection built in, so that means that if it's going to overheat, it will shut down automatically. Safe operating area, so it actually has a maximum current before it will shut itself down. And it comes with things like starting circuitry and current generators and so forth to make sure that this circuit works as accurately as possible. So by adjusting the resistance here, and therefore the internal volt drop, we can control, for any voltage coming in here, we can control what the output voltage will be within limits set by this particular device. And so let's have a look at what some of the characteristics of this device might actually be. So I'm looking at a very common one here, the LM7805, where the last two numbers give us the voltage. So in this case it's a plus 5 volt device. Now we see here the output voltage, typical 5 volts, with min and max. Normally these are pretty accurate, 5.01 volts or 4.99 is pretty reasonable. But we see we have parameters here that we've been talking about, the line and the load regulation. In this case, our line regulation, if our voltage in changes from 7 to 25 volts, we see our output voltage changes, note the units, by 4 millivolts. So even if our input changes by 18 volts, our output only changes by 4 millivolts. So that's quite incredible. Really small output change. Alright, we would get nothing like that with our original unregulated supply. With our load, if we change the output current from 5 milliamps to 1.5 amps, right, so it's a huge change once again in current, we see that the output changes only by 9 millivolts, the output voltage. So large changes in line or load result in very small output changes in terms of the output voltage. So it is a very accurate device that provides very good regulation, which is why these are so commonly used. The other parameter I want you to take note of is the dropout voltage. Now the dropout voltage here is a fixed voltage drop. Okay, it is never less than that across this device. So if you do have a 3-terminal voltage regulator, so that goes to ground, we'll have a capacitor, V in and V out. Let's say it's the 7805. If we want, for example, 5 volts out here, then with that volt drop, this is what's known as the dropout voltage, V in must be greater or equal to V out plus V drop. In other words, you are always going to get a minimum of a 2 volt drop across this device. That's what that dropout parameter is showing us. So that means our input voltage here must always be greater or equal to 7 volts in order for this device to operate correctly. If we supplied it with 6 volts, then we might get, I'm not sure, 4 volts out, or perhaps it might not even turn on at all. Alright, so the volt drop is a very important parameter when it comes to calculating what your input voltage range should be. And the solution is, if that 2 volts too much, then use an LDO, or low dropout regulator. Okay, and we can get those with, for example, 100 millivolts dropout across it. That's fairly common. So these are quite old devices, 7805, but they're quite robust and they can supply quite a lot of current. And they've got quite a nice large operating region that they can operate in. However, you can now get very efficient low dropout ones that work just as well for similar sort of money. But the first one I normally look at is the 7805 if it's one that we're going to, if I'm designing a new power supply. Alright, so line regulation, load regulation, dropout voltage are 3 important ones, and of course checking our output voltage is what we want. And the other really nice feature about these devices is that they have a very nice ripple rejection, which means that they actually internally filter out a lot of noise. Alright, so even just adding this guy in the circuit without the capacitors will actually filter out some of the noise coming here. Not a lot, and it's not going to be fantastic, but it will work a lot better than having it without it. Okay, finally, so when it comes to actually implementing this in your circuit, I've always got these couple of capacitors here, and we saw a couple of capacitors up here. How do you know what values they should be? Well, normally, always 2 to 3 capacitors in parallel with a 3-terminal voltage regulator. Now, it's quite nice that you can actually go back to the data sheet. So here's the LM7805 data sheet, and we can actually go through and it will give you, under typical applications, the suggested values of capacitance. So in this case here, all you have to do then is find these couple of capacitors, and sometimes it says they must have a low equivalent series resistance. That's fine, you can specify that from the manufacturer. Right, but normally 1 capacitor on the input, 1 capacitor on the output. If it hasn't been specified or you're doing a general design, I normally have something that looks like this. This is my standard configuration, where I actually have 2 capacitors on the output. So V in, V out, and I have a 10 mic here, 10 mic here, and 100 nanofarad here. So these get rid of the visible ripples, and this one is for the high frequency noise. And this is our 3-terminal regulator. So that's generally how I would design a circuit with one of these devices. Alright, so in this video we've had a look at the unregulated power supply and seen problems where the output voltage changes with output current, as well as we've looked at how the output voltage will change with varying input voltage. And we've defined those in terms of line regulation and load regulation. The solution was then to design a regulated power supply that has a constant output voltage regardless of changes in those two parameters. When we had a look at the Zener voltage regulator, however, we saw that while in principle it works for a constant load, if it doesn't have a lot of current, practically it is not a very good circuit, because a lot of circuits actually have varying loads or input voltages. And so the solution really is a 3-terminal voltage regulator or a switching power supply, which you'll look at in another course. But this 3-terminal voltage regulator, also known as a linear regulator, is a suitable choice. We had a look how these work in terms of these 4 main elements: the error amplifier, the reference voltage series pass, and resistor divider, and had a look at the characteristics of a typical device and how you would implement that in one of your circuits. Just remember that these devices do get hot. Alright, that voltage drop there, so power dissipated across this device is very roughly V in minus V out over I out, and typically anything greater than about a watt you're going to need to start thinking about heat sinking. It does depend on the device, and so have a look at the lecture that I did later on heat sinking for, as we see here, a typical linear voltage regulator.